samples are called independent from each other when the sample selected from one population is not related to the sample selected from the second population. Two samples are called dependent when each member of one sample corresponds to a member of the other sample. Dependent samples are also called paired samples, or they called matched samples. Very good. So how do we run z-test for the difference? A two-sample z-test can be used to test the difference between two population means, mu sub 1 and mu sub 2, when these conditions are met. So what are the conditions that we're looking at? First of all, sigma 1 and sigma 2. It means that the first population standard deviation and the second population standard deviation are given to us, either from past studies or somehow they know this information and they give us. Number 2, the samples are random, so they are randomly selected from the populations. Number 3, the samples are independent. Again, guys, go back to the definition of being independent from each other. Two samples are called independent when the sample selected from one population has nothing to do with the sample selected from the second population. And number 4, the populations are normally distributed, or the sample sizes are large enough. It means that N1, the first sample size, is larger than or equals to 30. The second sample size is larger than or equals to 30. So we have independent samples. They are randomly selected and the populations are normal, or we have large samples. In that case, the test statistic is the difference between the means of the samples. Well, remember what we did for one population hypothesis testing. We needed the standardized test statistic. So now that we have the difference between two population means, we also need a standardized test statistic, all right? What is that standardized test statistic? The standardized test statistic is denoted by Z equals to the difference between sample means minus the difference between population means, divided by, well, it's divided by the standard error of the test statistic, the difference between the sample means, which is square root of sigma 1 squared over n1, the first population variance, divided by the first sample size, plus sigma sub 2 to the second power, which is the variance of the second population, divided by n2, which is our second sample size. Well, now that we have the standardized test statistic, we can actually perform the hypothesis testing. What is the guidelines here? Using a two-sample z-test for difference between means, remember that the samples are independent from each other. If they are dependent, we have a different formula for that. 1, verify that sigma 1 and sigma 2 are both given. What is sigma 1? The first population standard deviation. What is sigma sub 2? It's the second population standard deviation. The samples are random. They are independent from each other, and the populations are either normally distributed or you have large sample sizes. Okay, what's the next step? State the claim mathematically and also verbally. Identify the null and alternative hypotheses. What is the level of significance? What is our alpha? Is it 1%, Is it 2%? Is it 3%? Is it 5%? 6%? 7%? 8%? 9%? 10% or more? Determine the critical values. If you're using the critical values, feel free to use the critical values. Then you can use the critical values to find the rejection region. Or after finding your standardized test statistic, you can find your p-value. Easily find the p-value and then compare your p-value and alpha. If your critical value is inside the rejection region, reject the null hypothesis. If not, you fail to reject the null hypothesis. Again, if your p-value is less than or equals to alpha, then you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. And finally, interpret the decision in the context of the claim in that question. Let's take a look at one example. So in this example, before I introduce the second formula, in this example, we have the following scenario. A two-sample z-test for the difference between the means. A credit card watchdog group claims that, hey, keyword, claims that there is a difference in the mean credit card debts of households in two states, California and Illinois. Okay. The result of a random survey of 250 households from each state, because the sample size is large enough, 250. Each state, we surveyed randomly 250 households. It's given in this little table for us. For California, the survey results in the mean of $4,777, and the sample size is 250. We surveyed 250 households. And in Illinois, after collecting the data, the mean of the sample is $4,866. Okay. Into the second sample size is 250. Very well. So we took random samples, and these are the information that we have. Remember the claim? The credit card watchdog group claims that there is a difference. Okay. You're the statistician, and we collected some data. From past studies, the standard deviations are given to us. Guys, sigma 1, the first population standard deviation is 1,045 for California, and sigma sub 2, the standard deviation, is 1,350 for Illinois. Do the results support the claim? When alpha is not given, remember we're using 5%. If it was not given to us, always use 5%. So what should I do? I need to follow some steps and do some calculations. These are the information that I have. Let us go back to the board and start writing the important information that we have here. Okay, let me make sure everyone can see. Okay, perfect. So, very good. So, step 1. In step 1, we're going to introduce the null and alternative hypothesis. Remember the keyword. The keyword was there is a difference. Okay, it means that they are not equal. There is a difference. It means that they are not equal. Not equal. They are not equal to each other. It means that your alternative hypothesis is given to you. This is your alternative, H sub A. Okay, so there is a difference between the mean of these two populations. H sub A says mu1 is different from mu2. And remember that this is your claim. This is the claim that we have. So put a little C in front of your H sub A, your alternative hypothesis, to represent the claim. Well, my null, they are equal to each other. Mu1 is equal to mu2. So remember that by looking at the alternative hypothesis, we know that we have a two-tailed graph. I have a two-tailed graph. Either using the rejection region or p-value, both of them give you the exact same result. So your p-value is divided into two areas, one area to the left, one area to the right. Okay, what is my step 2? In step 2, I need to find the standardized test statistic. Standardized test statistic. We have a formula. We just learned about the standardized test statistic. We learned that Z is equal to x1 bar minus x2 bar into parentheses minus mu1 minus mu2 divided by, well, on the denominator, they have some calculations to do. Square root of sigma 1 squared over n1 plus sigma 2 squared over n2. Okay, guys, remember that your samples are independent from each other. People who live in California, they don't live in Illinois at the same time. So the samples are independent from each other. Samples are independent. That's why we are using this formula. Samples are independent. Okay, perfect. So let's do the calculation. Our Z is equal to, let's go back to the note. What do we have in the note? X1 bar is 4,777 minus, and x2 bar is 4,866. Let's put that in parentheses and let's look at the rest of the data that we need, the information that are given here to us. So let's go back to the board and enter all of this information. So x1 bar minus x2 bar minus the difference between mu1 and mu2 is 0. Mu1 minus mu2 is 0. So you can just at the beginning cross this off and say it is 0. Divided by the square root of sigma 1 squared over n1. Sigma 1 is 1045. So 1045 to the second power over n1, which is 250, plus sigma 2 is 1350 to the second power divided by 250. Very good. If we use our calculator, it gives us approximately around -0.82. So this is my standardized test statistic. Standardized test statistic. This number is right here, -0.82. I'm going to use this number and find this little area here. So I'm going to use my second vars and then go to normal CDF. My lower limit is like -10. My upper limit is -0.82. Mean is 0 with standard deviation 1. Okay, let's see what is half of the p-value here. Let's turn on the calculator. Okay, perfect. Second vars, go to normal CDF. Lower limit -10, so -10. Upper limit is 0.82. Mean is 0, standard deviation is 1. So this little area on the left is about 21%. So 21%, multiply that by 2. It gives you 0.41. So a half of p-value is 0.21. And so p-value is going to be 0.41, about 0.41. So now compare p-value with your alpha. P-value and alpha. Alpha is given to us as 5%. Am I right? There we go. P-value is 0.41, which is larger than your alpha, which is just 5%. So since p-value is larger than alpha, we fail to reject or interpretation. We support the null hypothesis. So we are supporting the null hypothesis. It means that we are rejecting the claim. So since we support the null hypothesis, we reject the alternative hypothesis, or in this example, the claim. So after doing all of these calculations, you can also double check your work using a calculator. So let me erase the whole thing here on this side. Hypothesis testing for two populations. You're going to go to stat. You're going to go to test. So let me write calculator here. Calculator. Go to stat. Go to tests. Now you're going to select two sample z-test. Two sample, we have two sample and it's a z-test. Two sample z-test. Okay, perfect. So we don't have the actual data, we have the information that are given to us. So we're going to select stat and sigma 1. What is the very first population standard deviation? It's 1, 0, 45. The second population standard deviation, 13, 50. And x1 bar, the first sample mean for 777. And N1 is 250, sample size. X bar for the second sample is 4866. And the second sample size, 250 as well. And here you have a two-tailed hypothesis testing. So you're going to select mu1 is not equal to mu2, okay? And then that's it. Yes, let's do the calculation. See what do we have. Okay. As you can see, here you have your z, which is negative 0.82, the same z that we got. Okay, we're good, we're happy. The p-value is about 41%. Our p-value is also the same, 41%. So we did all of the calculations correctly. We're happy about what we did. The calculator actually confirms our calculation. So we're happy. So calculator also confirms our calculation. It means that we didn't do any mistake. Everything is done perfectly.